Welcome, and thank you for joining me today for my presentation. My name is Derek Dean, and I'm the Vice President of the SCADA and ADMS departments in ETAP. I'm excited to present to you today ETAP's latest solution for analyzing and reporting on faults on a transmission network, the ETAP AFAS, Advanced Fault Analysis Software. With its powerful analytical capabilities and user-friendly interface, ETAP AFAS offers a comprehensive solution for fault analysis, helping to minimize downtime and maximize productivity. Let's dive in and explore this innovative software in more detail. I'd like to start by quickly discussing the agenda for this presentation. We'll first discuss the challenges faced by the industry, including outdated systems, lack of automation, and the increasing complexity of modern networks. We'll explore the various solutions that have been developed to address these challenges to date. We'll dive into the motivation behind our product and how it solves the challenges faced by the industry. We'll provide a detailed overview of our solution, including a technical breakdown of how it works and how it can be implemented within existing networks. We'll give a live demonstration of our software in action, showcasing its capabilities and ease of use. Finally, we'll wrap up by discussing the value proposition of our solution, including how it can help organizations reduce costs, improve efficiency, and enhance safety and reliability. Here's some comments I've received from customers in the industry. It can take hours to locate a fault, especially in more rural areas. And depending on the specific regulatory requirements and complexity of the fault, it may take anywhere from several days to several weeks or even months to create a post-fault analysis report. As you can see, there is a major potential for saving time and resources by implementing the right tools. Prolonged outages can have severe consequences such as loss of power supply, resulting in disruption of daily life, financial losses, and potential safety hazards. Damage to equipment can lead to costly repairs, replacement, and extended downtime, negatively impacting the reliability and performance of the system. Reduced reliability can impact customer satisfaction, damage reputation, and lead to compliance issues. Safety hazards, such as exposure to live wires or lack of emergency lighting, can pose a risk to human health and life. Environmental impacts, such as pollution, waste, and contamination, can have long-lasting effects on the ecosystem and public health. In the current industry landscape, users often face challenges in fault location and analysis, including the need to travel to substations to download events, relying on hand calculations to determine fault currents and voltages, and using pre-calculated sheets or software to estimate fault parameters at various locations on the network. It's more of a guess and check and lookup tables. Additionally, some hardware solutions provide single-ended fault location, which may result in inaccurate or unreliable fault location results, further complicating the process. These challenges can result in extended downtime, reduced system performance, and financial losses. To overcome these issues, there is a growing need for advanced fault location solutions that leverage real-time data and sophisticated algorithms to improve fault location accuracy, reduce downtime, and enhance system performance. The motivation for this solution stems from the synergy of existing technologies at our disposal. Firstly, we have the digital twin, which already stores all of the necessary electrical information needed for AFAS calculations. Secondly, the STAR-Z module provides the essential algorithms to calculate fault information and protection responses. Thirdly, we have the eProtect system that efficiently manages relays in a centralized database. By leveraging these technologies, we have been able to develop an innovative solution that combines their strengths and provides a comprehensive and efficient fault analysis tool. ETAP AFAS is an enterprise solution that helps engineering and operations teams manage electrical faults. It provides advanced capabilities for fault identification, location, analysis, and reporting, maximizing uptime, enhancing performance, and minimizing costs. ETAP AFAS integrates real-time data and advanced algorithms, empowering users to work efficiently, collaboratively, and achieve improved results. If you've attended any of my presentations on AFAS or eProtect before, you're likely familiar with this image. It highlights the crucial role that AFAS plays throughout the entire life cycle of a relay. First, we use the ETAP desktop client to model the electrical system and ensure that the as-designed settings are accurate. To validate these settings, we employ STAR and STAR-Z for protection and coordination studies, which ensures reliability and efficient protection of your system. Next, we can seamlessly integrate with the relay's software to download the as-found settings in the field, eliminating the need for manual data entry and reducing the risk of human error. This enables us to identify any discrepancies between the validated as-designed settings and the actual as-found settings, ensuring that the proper functioning of the relays and maximizing system uptime. Using relays test sets, we can run disturbance simulations and save the as-tested results to the eProtect database for further analysis and record keeping. This ensures that you have comprehensive data on the performance of your relay during various fault scenarios. Lastly, leveraging the innovative AFAS solution, users can obtain the as-operated response of the relays, providing valuable insight into their real-world performance. This data can again be saved in the centralized eProtect database for further analysis and comparison against the as-tested response, enabling you to identify any performance issues and taking the appropriate measures to address them. All of this information is securely stored and managed on-premises or on the cloud using the ETAP eProtect solution, ensuring that you have access to accurate and up-to-date data throughout the entire relay lifecycle. This shows how AFAS plays a crucial role in the lifecycle of the relay. ETAP AFAS is designed on the same platform as ETAP SCADA, utilizing its advanced communications capabilities to enable real-time data acquisition and processing. It is equipped with alerts and notification that promptly inform operators of potential faults, empowering them to respond quickly and mitigating the impact of the outages. With its crew management and dispatching capabilities, it efficiently deploys field personnel to perform repairs and maintenance. ETAP AFAS offers clear fault information visualization on SCADA screens, enabling operators to identify faults and take corrective actions. Its built-in waveform viewer also facilitates further analysis. Together, these features boost the reliability, safety, and efficiency of your electrical system for your organization. ETAP AFAS provides a comprehensive fault analysis capability, which includes disturbance record analysis, fault severity analysis, and fault location. It also provides the as-found field sequence of operations and line impedance to furnish operators with a complete understanding of the fault response of the system. Through the as-designed ETAP sequence of operation, operators can compare the actual fault response with the anticipated response, which enables them to identify any discrepancies and take corrective actions. These capabilities enable organizations to quickly and accurately diagnose faults, reduce downtime, and enhance the reliability of their electrical systems. The eProtect integration serves as the central repository of all relay asset information. Additionally, the calculation of the reach diagram and optimized distance protection settings can be determined using the eProtect solution, which is a valuable benefit to the AFAS solution. Lastly, the ETAP AFAS solution provides post-event analysis reporting that includes all details related to a fault incident, including the pre-fault, fault, and post-fault conditions, executed relay protection schemes, affected areas, relevant calculations such as fault location, fault type, fault current, fault voltage, and much more. AFAS is a powerful solution that performs various calculations to analyze and report on faults in a transmission network. It starts with disturbance record analysis, where it segments the disturbance record into pre-fault, fault, post-fault, and dead conditions, and calculates fault severity metrics such as the fault current and fault voltage. It then performs model-based calculations to determine the fault location using various algorithms such as single-ended reactance, single-ended Takagi, multi-ended synchronous, multi-ended asynchronous, and multi-ended synchronous parameterless algorithms. Additionally, line impedance information is extracted from the digital model. Lastly, AFAS offers model validation by comparing the relay protection scheme as operated versus as designed by placing the fault into the ETAP model and providing the ETAP-generated sequence of operations which can be compared against the field-generated sequence of operations. And signal injection allows users to play back recorded data in the protection model for further comparison. Overall, AFAS provides accurate and reliable fault analysis for transmission networks. Next, let me briefly walk through the program together. Here is our standard web user interface, which takes into account Windows Active Directory. So if you have Windows Active Directory set up, you don't need to create new users. Everything is stored in one centralized repository, and we're leveraging all of the security that Windows Active Directory benefits. However, we do have a user access management tool on top of that, which provides role-based authorization. So our authentication is through Windows Active Directory, and our authorization is through our own user access management tool. Here, as this is a web user interface, as long as you have access to the web server, you have access to eProtect or the AFAS. Now, note that this doesn't, just because it's a web page, that doesn't mean it's necessarily required to be on the internet. This can be on your local intranet, your corporate network, or even in a very secured location where no one has access unless you're on a very strict secured network. So this even though it's on a web page, it doesn't necessarily mean that it's on the web. So first I will log in with my credentials here and navigate to the AFAS main page. Here you can see past reports incidents. So I just have one incident in this page here, and it was on the 22nd of June in 2021. But it's important to note that you can go back into the past and see all of your incidents through time. We don't delete anything, and you'll always be able to pull open an older incident and navigate through using the calendar selector here. Users can add their own custom labels or view the waveforms associated with any incident. For this incident, we can see that it started on the 23rd, and here we can see some of the details about that incident. First, the field sequence of operations. Let me expand so we can see all of the digital signals that came from the disturbance records. So here you can see the time that the trip signal was detected and when it went false. You can see here also that this specific incident is a reclose operation because it went to true, then to false, then to true, then to false. So the initial conditions was true, but then it tripped, and then it reclosed, and then it tripped again. Here you can see there's many other signals that we can bring in from the disturbance record. So this is the raw data from the disturbance record from the relay. Now I can go into the fault location section. Here, again, I'll show everything. Here we have multiple different ways of calculating the same fault location. So here we have the component name. So this is line L1, the bus where the fault, the from bus, so one side of the fault on the faulted cable, and the to bus, which is the other side of the faulted cable. This allows us to understand what distance from what bus is the fault. If we can determine, we get the fault type. So here it's an A to ground fault. The line length, now this is extracted from the digital twin. The distance. Now you can see here that you have various different values for the distances. And this is because each algorithm has its own its own strengths and weaknesses. So for instance here, the single-ended Takagi provides a 75.03 as the distance kilometers away from the TOM 230 bus, whereas the single-ended reactance gives me 79.93 kilometers away. So the important thing here is when we're looking at single-ended calculations, here these first few are single-ended calculations, they're typically significantly less accurate. That means you only have a relay on one side and you calculate the fault location based on the relay on the one side. Now if I look at my multi-ended calculations, they're all within a very small distance of each other, 75.01, 75.06, 75.09. So these are all very close, indicating the accuracy of the calculations. And this is reflected here if you look in the standard deviations. When we're looking at the single-ended side, the standard deviations are much higher than on the multi-ended side. So this reflects back to what I mentioned earlier when we look at, let's say, relay protection protection relays which provide a fault distance. This is only using the single-ended calculation. So this is not going to be nearly as accurate as the multi-ended calculations that we have here, where we can take in the disturbance records from both relays on each side of the line. In addition to the distance, we provide the distance percentage, which gives you a different way of seeing that information, and as I mentioned earlier, the standard deviation. Next, we have the relay data. So here, again, let me expand this out and show, oh, I am showing everything. Okay, so here we can see each ComTrade file that we received. So we received a disturbance record from relay L1 TOM230-A, and then we received a disturbance record for L1-Weber-A. So what's important here is we take that ComTrade file or that waveform and we analyze it and separate that waveform out into various zones. So for instance, load flow is the initial condition, and here you can see for both L1 TOM230-A and L1 Weber-A, the initial state is that load flow. So it's the initial conditions. What are our normal operating conditions? Then we move on to the fault state. For both of these ComTrade files, we see the fault state. So when we hit that fault, here you can see my voltage and my current. So here, as I saw earlier in my fault location section, we calculate that it's a fault of A to ground. So if I go back here and if I look at my A phase current, here it's significantly higher than my B and C phase current here. And my voltage is significantly lower than my B and C phase voltage. So that tells me that we have a fault on the A phase, and here's what the characteristics tell me during that state. Also, if you look on the L1 Weber A during that fault, you can also see our fault current. So it's different fault currents seen on each side. Now, then the line goes dead. So this is the relay protection comes in and trips off the relay. And then we see another fault. That's because we reclose. So we close up the circuit breakers just to see if maybe the fault was has been isolated or if it was a temporary fault. And here we can see, because the next step is dead, that again, this is a permanent fault, and that we are seeing that the entire system, that entire line is being de-energized. Now, when I go into the fault severity analysis here, you can see it may be confusing, but there's two faults. There's two elements in this, and both on line 1. That's because this is not a temporary fault, it's a permanent fault. And here we show the times that these different events happened, the fault current and the fault voltage. And so the first one is the initial fault. The first record is the initial fault. The second record is the reclose fault. So we really break down into all those different components. Next is the ETAP sequence of operations. So here, and let me hide my events here so we can see all the details. So here we break down, we actually take the fault, let me go back to the fault location here. We use the multi-ended synchronous results, which are the most accurate, if we have them, place that fault in the ETAP model, and run a star-Z protection coordination study, and find my sequence of operations as a result of this. So here I can see in the ETAP sequence of operations that my first steps are after 16.666 milliseconds after the fault occurs, the trip signal has a relay output signal for the logic to go on. So after 16 milliseconds or 17 milliseconds, we're executing a trip signal. At the 50 millisecond mark, we have CB17 and CB8 are tripped. And then at the 166 millisecond mark, we have a BF trip as part of the relay protection logic, which causes these other 5 circuit breakers here, 27, 29, 44, 47, and 48, to also trip off due to that bus fault trip protection. So here we can see this is what the ETAP model predicts should have happened, and you can compare that against the field sequence of operations, what is seen there, as well as what was seen in the SCADA. So we have our as found versus our as designed settings, and here you can validate the logic that has been put into the relays and the logic that is in the ETAP model, and make sure you have the most accurate ETAP model and that your protection settings in the field are correct. So this is, in general, my AFAS results. From here, you can generate reports which contain all of this information and more. Additionally, we have the waveform viewer. Let me see if I have it here. Yeah. So in our waveform viewer, any ComTrade file or disturbance record that's received, we can visualize that in our waveform viewer here. Let me go ahead and open one up. So this one may not be very interesting. We can define what are our phases. We automatically extrapolate what we can from the file itself, but we can actually go in and explicitly define that the value 1 from the ComTrade file itself is my A phase, and we can automatically define, here's my voltages, here's my currents, and so we can very clearly define what we have in the system. Now here, this is, there's not much at all current, and the voltage is pretty consistent here, but we do see some digital signals as well here. So my IC1 turns off at this time, or turns on at this time, and my IC1 CB closed at this time here, and I can actually add my yeah, here we go. My tracker for time and value, but yeah. So this is the ComTrade file waveform viewer. You can add and remove whatever signals you'd like in here. So I can add new signals. I can create new charts. So I have my current, my voltage, and my digitals, but I can create new ones. I can do calculated tags, so RMS value calculated tags, phasor calculated tags, frequencies, all sorts of information you can bring in here and visualize to slice and dice the data with whatever way it makes sense for you. Lastly, the value proposition for a user of ETAP AFAS can be summed up as follows. First of all, improved efficiency. In collecting disturbance records by implementing streamlined processes and tools, automate the collection of data from various sources, such as protective relays, SCADA systems, and event records, to minimize manual effort and reduce the risk of errors. Utilize advanced fault location techniques to quickly and accurately pinpoint the location of faults, incorporate intelligent algorithms to analyze fault data, and provide automated fault diagnosis. Adopt standardized report formats to simplify the creation of post-fault analysis reports. Leverage data visualization tools and dashboards to enable efficient data analysis and interpretation. Implement a fault database to store all fault records and associated data, including fault location, time, duration, and severity. Enable easy searching and retrieval of past fault records to facilitate historical analysis and trend identification. And perform regular validation of protection schemes by comparing the as-found system response to the as-designed response. Use advanced simulation tools and models to simulate fault scenarios and evaluate the effectiveness of protection schemes. Incorporate feedback from validation exercises to continuously improve protection schemes and enhance system performance. Thank you for your time. Don't hesitate to contact me if you have anything else that you'd like to discuss.